JP Skeath will be our speaker today. Many of you may know or have met JP, but he is the NERC Manager of Engineering and Security Integration. He has been tasked to identify risk and design solutions to emergency energy problems. He works with several NERC reliability and security technical committee subgroups, the RSTC, those subgroups, including the system planning impacts of Distributed Energy Resources Working Group, known as SPIDER-WIG, and the Electric Vehicle Task Force, the EVTF. JP leads a small team of engineers that are tasked with identifying, validating, and mitigating emergency risk in the areas of frequency, large loads, distributed energy resources, and inverter-based resources, among other specialized topics. If you give me just a moment, I will share my screen and we will get started with JP's presentation. After we finish with JP's presentation, we will open it up for questions. You're welcome to submit those questions as we go along. We will circle back and present them. I also have a couple of general announcements that I will circle back and pick up at the end of after JP's presentation. So are you able to see the slides?
Thanks, Mike. Yes.
All right, JP, take it away.
Looks like there's a little feedback. It might be coming up. All right. Thank you all, and thanks for having me, Mike, and the RF team. Excuse me. As Mike said, I'm the manager of engineering and security integration inside NERC. I report to Latrice Harkness, if you know a little bit of our structure, but what I like to say is I share that title with another manager inside that team, and I'm the engineering side of that, and the other manager is the security integration part of that. So I am excited to kind of build off of the last presentation discussing frequency response, and particular frequency participation of IVRs inside the system perspective. So I'm going to present this from the system perspective, and the way that the changing, I guess, in frequency response may be related to underfrequency load shedding requirements, or that safety net that we have as a last-ditch effort to arrest frequency and rebound before system collapse. So this slide is largely just showing how NERC and the system approaches frequency response and the needs for various different products within certain periods post initiating events. So whereas Daniel's presentation kind of showed from the IVR perspective of the ability to provide, this is where, when we in aggregate see the interconnected systems respond, we have a very known period within the I guess median or even localized frequency that shows the various ways that we measure. So on that picture there, you can see that there's a few different points, A, B, C, D. A is the initiating part, the event, whereas we have in that first period of arresting, we have basically an inertial response that limits the rate of change of frequency in the arresting period before it hits its lowest point, point C, the nadir of the response. It recovers a little bit based on our history, and then essentially stabilizes within the first 52 seconds following the disturbance. And so the arresting period goes into a rebound. At the point B is in between that point C and all the way to point D, the end of the primary frequency response evaluation period. And then D is the ending frequency of that period, where we start getting into secondary frequency control, which includes things like AGC. So this is considered one of our essential reliability services, and that's what the report is on the other slide, among other items. So you can see voltage support, which Daniel also talked about earlier, and I wanted to also call out net demand ramping. So this is a unique type of response that we evaluate. It is not necessarily the same as the generation commitment and dispatch that we would have to meet future year demands. Sorry, not future year, future hour demands. I'm a planner by trade, so when I say future year, I usually think, oh, that's the next iteration I'm going to do the study. Well, in the generation and load balancing, we have this as net demand ramping, and so we would need in the next few hours to be able to meet our demands. And so this is distinct from the generation scheduling that is needed in order to meet interconnected reliable operation of the system. Can you go to the next slide, please, Mike? All right, and so this relationship to that inertial response or rate of change of frequency response, I kind of want to call out that while historically we've taken a look that is the inertial response that's limiting the rate of change of frequency, that is because of the synchronous machines. And I think one of our questions earlier was related to, well, if it's a synchronous machine, it can provide some sort of immediate response, and that is true. It is providing a damping, but rate of change of frequency is not the same as inertia response. Inertia response is very similar to a frequency damping effect, however. So the way we measure rate of change of frequency is at the initial start of an event, and half a second later, we'll look at the difference between those 2 points, as that is the initial response of the system immediately following the disturbance. So with higher inertia, we expect to see lower rate of change of frequency. And with lower inertia, we expect to see higher rate of change of frequency. And that is a relationship that those two have, but they're a little bit of a distinct aspects when we talk about how do we solve very fast rate of change of frequencies before we hit things like under frequency load shedding. So the equation for Rokoff that we have is there. You have it's impacted by the size of the event as well as the kinetic energy of your system in the historic context. So the damping for the loss or the change that is occurring on your system is in the denominator there, and it's measured as such. We report that in our frequency response annual analysis, and I will talk about that later. But next slide, please. Where we start to see concern, especially from the system perspective, is when that lower point, that point C nadir, starts approaching the first stage of under-frequency load shedding. So we have standards that the most single severe contingency or the most credible single severe contingency for multiple or sizable generation loss, that does not engage your under-frequency load shedding. That's typically how we analyze and what we would want to avoid. Under-frequency load shedding is designed for an imbalance of up to 25% difference between a formed island for the under-frequency load shedding program design. And so we want to see typical frequency response for the most single severe contingency in a normal operating state to not hit the first stage of that under-frequency load shedding program. So we've identified very particular purposes of each of the four discussed periods. So the frequency response is broken out again into that arresting, rebound, stabilizing, and recovery period. So while inertia or other damping can be involved in the arresting period, the primary job of that period is to stop the frequency collapse and the frequency decline. And so that'll hit a low point and it'll start rebounding. And so if we have initially a fast recovery, that period in the point C will be higher. And you might see a lesser of a recovery if we have non-sustained initial frequency response. So now we move from the arresting period into the rebound period that has recovered our frequency from its lowest point, but it is, we might see some limitations on that initial burst of energy. As the frequency starts to stabilize, we approach that stabilizing period. It's not normal. It's an off nominal frequency, but it's holding steady. So it's not in collapse. It's not recovering fast. There's not a secondary control that's trying to bring it back to nominal just yet. And so we start seeing secondary frequency controllers begin to pick up this off nominal frequency and begin processing that in their next set points and next dispatch signals for things like AGC. And that's where the recovery period slowly but surely brings it back into the deadband operating range around your nominal frequencies. So next slide. As you can see, that's where our periods, and we're trying to design that so that under frequency load shedding is not enacted as part of this typical response. And so under-frequency load shedding is dictated in PRC6. PRC6 has these charts where essentially you need to model specific tripping of generation resources above the under-frequency set points, as well as below over-frequency set points for specific generators. So to show a little bit of the difference of the line, the inner lines are the performance criteria for the simulation, whereas the model criteria is the outer red lines. So that's essentially saying you must model specific generation tripping that may occur underneath the over-frequency load shedding and above the under-frequency load shedding for these types of simulations, to show that if there's other resources that will trip as part of the simulation, those will need to be included as part of the study. And so that's a bounded period. However, the under-frequency load shedding performance criteria mean that your program, as designed by our planning coordinator, needs to make sure that the simulated frequency remains between these boundaries during this time period. So the chart is on the left to show it graphically, but the values that are mathematically calculated to show those lines, those are to the right. And so you can see for under-frequency the under-frequency ones are over to the right. Those aren't the over-frequency curves. But for under-frequency load shedding, we can see that 59.3 is essentially where, for the entirety of the simulation, for however long the program would last, needs to stay above 59.3 after that initial broader section. And that's where we can see where some of the first stages of UFLS actually are, is 59.3 or 59.5. So for most of our UFLS and our frequency response programs, we want to make sure that the first stage of UFLS, typically around 59.3 or 59.5, are not hit within our typical frequency response events. So how do we wrap all this up into a concise report as we're taking a look at various different data sources, various different aspects, and approaching the various different ways to describe points A, B, C, and or D. And on the next slide, we aggregate all of that reporting on up into our frequency response annual analysis, which is our report of showing how each interconnection is addressing various aspects of interconnection-wide frequency response. Does it hit, and is there a margin from that lowest nadir to the first stage of the under-frequency load shedding? And if there's other significant events that are taxing our large-scale frequency responses, or are we getting close to the MSSC for that design? And so you can see there, the frequency response annual analysis holds the data that build our adequate levels of reliability metrics, the left-hand side of the slide here, where we show the statistical changes of these very large events. So the M4 events, this is measure 4, essentially show, is it a big enough event to statistically be different from the rest of our frequency obligation type events? That's essentially, does it reach to the point of a large enough disturbance that it's close to the MSSC, and thus design or test the designs of our frequency response obligation that is housed within our FRAA report that's on the page there. The snapshot here is what's currently public on that link. So you can see that our 5-year statistical trend is showing for the Texas interconnection, which has quite a significant capacity of wind and solar resources now, is actually seeing an increase in their response and their inertial type response. So we're seeing that by increasing demand or damping of frequency response, including even in potentially IBR-rich areas, we can actually see an increase of frequency response in order to arrest frequency decline for large-scale generation losses. On the next slide, I think this is taken from one of our older reports, but I think Daniel actually had a better way to also describe this from the generator's perspective. Is essentially FFR is primary frequency response, but faster. So one of the ways to really describe this is its energy injection prior to the nadir of your frequency event. So are you able to provide some frequency response very early on? So that includes the synchronous inertial response, which is an inherent property of the machine to arrest changes in frequency, also known as just frequency damping. If that is sustained even for a short period, you can be a fast frequency response as defined by many of the different FFR functions enabled in IEEE 2800. And so I just kind of want to describe that primary frequency response is inherently it starts from the beginning of the event, and that's what the left-hand side is, and it's a sustained type of control that will be evaluated over that period. Earlier in the slides that I presented, it is designed to be sustained, but some fast frequency responses can actually provide a lot of energy early, but not sustain that for the entirety of the frequency excursion. So there's many different ways and various levels of control here to maintain a stable frequency, as well as improve your frequency response. So our measured points are those A, B, C, Ds in the arresting, rebound, stabilizing, and recovery periods. And so early on energy injection in a frequency event can raise your point C, your nadir. And so that will improve your C to UFLS margin and thus improve your frequency response, even if you don't really change the period where you're stabilizing. So various metrics around here, but I just want to really highlight the point that essentially FFR is PFR but faster, or energy injection prior to hitting the nadir point of your frequency response. So let's go to the next slide. I realize I left off the title here, but I really wanted to describe this as, okay, so what really is the point of why do we have slow time delay or time delays in hitting a nadir? And why can we speed up controls in order to inject energy prior to reaching a nadir? And so I kind of want to take us back to the speed governing type controls of typical steam type plants, where a lot of our synchronous facilities were originally based on. We had a lot of coal early, so most of this control and a lot of these concepts were kind of developed and their teeth got cut, and now we see that in even gas turbines and other types of speed power controllers. So the above loops are essentially showing the prime mover hitting the generator, and so you have a specific change in mechanical power that's derived by the injection of steam into this valve. And so these valves were controlled through that feedback loop of the actual loading of the generator. So the generator would have a speed sensor that could then change the shaft speed into an electrical frequency. That electrical frequency was monitored and put into a load controller to show that this is going to then control various loads. As the load changes, it's going to try to find that set point and adjust how much steam is going into the prime mover. Well, that steam valving does take some time to change. So none of these changes are instantaneous because we're moving mechanical parts. And so on the next slide, I wanted to just highlight each of these time delays add up. And so while this could be a very sustained response, it can be slow because it takes time to move each of these pieces throughout this loop. Whereas IBRs are largely software-based. So while there are limitations and there are time delays, they are faster than what is typically out there today. So when we're talking fast frequency response, we're essentially saying more of the modern IBR controls, you can achieve this in some synchronous plants, but we're essentially basing it off of the historical perspective of very slow time delays to hit your frequency controls or your speed load controllers from our generation fleet from the past. So what is the types of fast frequency response that we're really talking about? Can we use this example and kind of springboard? What does that kind of look like? So on the next slide, we at NERC went through and just kind of thought up other types of that FFR and what that could look like. So on the left slide, you can see the frequency excursion of the typical nadir into recovery or stabilizing into recovery period, and the types of fast frequency response that we'd see. And so essentially energy injection prior to the nadir was considered FFR at the time of writing the paper. And so you could see load coming offline, as that reduction of load would help recover the frequency faster. So a very fast load disconnection that's not tied to under-frequency load shedding may help. So if like a battery energy storage system that is currently charging drops offline for that period of a frequency excursion, that will help in the system's recovery of frequency. Similarly, we have synchronous generators being able to provide, like either with fast valving or some fast valving with governors, to be able to provide more than just an inertial response, but either non-sustained or even sustained fast frequency response prior to that nadir point. And then you can kind of see where IBR-based approaches can be a step change or ramp. There's a proportional inertia-based FFR that can come from wind plants. No matter the type, energy injection prior to the nadir can assist with the frequency response. And so I just wanted to show that this is the graph that shows with various percentages of IBR in the system, so up to 80% instantaneous penetration versus an all synchronous with various delays. So the blue line is just your standardized 100 milliseconds delay. Now, if you increase that to 1 second, so say we had slower response, we would actually see a lower nadir. And so really, when we see that point C, it's not necessarily just rate of change of frequency. So we had the same amount of inertia on the system, but it took the actual governors more time to react to the changing frequency. And it lowers when you have additional time delays in that control. Now, you could speed up that control, and IBRs are capable of that. So you can see the red line of 80% IBR with 1 second delay. So we're going the slowest possible delay, but it's 80% IBR control. Well, that tanked to the 59.5, and that is typically below the first stage of UFLS. So that would be a significant problem. So what happens then when we speed it up? Well, that's your orange and your green line, and green is having that, and then red is a very fast 10 millisecond response delay from the active power frequency controls in the IBR plant. And you can see the nadir rises to the point where we're no longer at jeopardy of hitting under frequency load shed, but it does come with some issues. You can see that those are more oscillatory. You see that as the system reduced its inertia, we now have lesser damping to the frequency changes. So these fast injections are felt throughout the system, and so we're seeing additional oscillatory behavior. You can kind of see that when we also adjust the synchronous response, the synchronous delay, but it is damped out by the additional inertia on the system. So that's where we start seeing FFR as well as frequency damping in the system interrelate. We can have very fast FFR that improves our nadir, but we may start seeing oscillatory response if we do not have a certain level of inertia. So on the next slide, I just kind of want to walk through these three concepts as I've walked through the relationship of fast frequency response, inertia, rate of change of frequency. So this was provided to us by ERCOT during the time of writing our initial thoughts on FFR from the IRPS. And this really shows how they derive their critical inertia. But it's an analysis that says, okay, what at various inertia levels and the percentage that I have of fast frequency responsive units, what does my rate of change of frequency look like? And so as you can see with lower amounts of FFR, our rate of change of frequency will increase from our IBRs that are there as we reduce our inertia, green line being highest, blue being lowest. So the blue being a higher IBR dominated grid, we will need added FFR to ensure, we would need, let me make sure that I remember this chart correctly here. As you can see, the rate of change of frequency to the left for a 300 megawatt contingency with the percentage of units not having FFR is where this is looking at. And so as you increase that, if half of your IBR units do not have FFR, you are going to have a significant rate of change in frequency and being unable to sustain that loss. Further, as you increase your inertia, you don't need as much FFR. So in higher synchronous penetration environments, you will not need as much FFR for the same contingency size to have that same level of rate of change of frequency. So increased FFR capabilities reduce the needs for inertial response. However, Rokoff is still impacted by that lower inertia. And so you can see all the way even on the left, just by changing your inertia, ERCOT was even showing your rate of change of frequency does change. It can be sustained for longer as you have higher inertia and additional FFR capabilities, but it is still impacted by, even with all units providing FFR, the initial rate of change of frequency. And so that kind of shows a little bit of a balancing event, a balance of trade-offs and cons here. Next slide, please. On one side, sorry, Mike, can we switch? Yeah, thank you. On one side, we see a reduction of inertia and frequency damping due to the increasing penetration of IBRs on a grid, or a changing inertia or resource mix. It reduces the frequency response of the rest of the system. However, these facilities are vastly capable of providing fast frequency response. That capability is a dramatic improvement for our frequency response and the way our interconnection responds to frequency disturbances. Further, there's a kind of a tertiary effect of an increasing IBR penetration grid, where there might be many additional synchronous units not at maximum capability. So we actually may have we might have higher sustainable limits for our synchronous fleet in this changing grid as we begin to transition. So we might see improved frequency response during this grid transition if we enable fast frequency response and other frequency responsive generation. But that reduction of inertia / damping is kind of a concern. So there's a balance here. And so I kind of want to describe this trade-off in a pretty good analogy. So on the next slide, please. This is the type of generation that we would receive from our synchronous generators. So I like burgers, and I think this might be shared by many of us. And so this analogy does break down if you are a vegetarian or do not like meats and cheeses mixing. But for those of us that do and love burgers, this is something that we all go for. There's a certain craving that these ingredients bring together. So a synchronous generator is essentially like this burger. It provides the essential reliability services without the explicit requirements because of what it provides in being a burger. It'll have the lettuce, the cheeses, the toppings that can be enabled or disabled. Some of us like tomato, some of us don't. But when you think of a burger, there's an essential amount of components that are coming together to provide some services. And that includes system strength and inertial response. And so these are kind of tied together by the inherent design and operation of these facilities. Now, on the next slide, we've been talking about fast frequency response. This can be done by both grid following or grid forming IBRs. And so a grid following IBR is kind of like this plate of salad. So if you're thinking of a burger, you can have a burger salad, but if you don't have the components that make up a burger in your salad, you don't have a burger salad, you just have a salad. And so while this is a tasty meal all of in itself, it is providing some of those essential services when explicitly required. And you can see that some of these are actually shared with our synchronous facilities. And if we go to eat our veggies from burgers, we're not really getting all of our servings of vegetables. We actually should go to more nutritious meals for these types of work. So if we're trying to get our daily share of veggies by just eating burgers, we're going to fill up on other things before we actually get to that share. So there's a balance here. As we say, eat a balanced diet. This can show where inverters that are highly capable of providing these types of services can be used in a full set of system design. What's not presented here is grid forming inverters, which can also add added components to this meal. So say we're missing the cheese. We can add cheese to a salad. that is a grid forming inverter essentially, where we're taking a grid following inverter and adding additional either controls or capabilities or inherent design in how it's operated to ensure system strength of the local area, not just through dynamic voltage support or faster governor or FFR responses, but actually providing a damping and increasing system strength of the local area will assist in being able to enable the rest of these enhanced capabilities. So on the next slide, I just kind of want to leave us with a few key takeaways so that way we're not just looking at food. I just want to leave us with fast frequency response here as being an important part of all frequency excursions so that they do not enable the first stage of UFLS, and I'm sorry for the typo there. As I mentioned before, the PRC6 requires less than a 25% imbalance, but fast frequency response and enabling that fast frequency response ensures that our frequency excursions are still within that similar design parameter. And we saw that from the chart there earlier. The increasing penetration of IBRs or the grid transformation serves as that potential double-edged sword. There's a balance. We have an increasing frequency response due to fast injection of power capability and enabling that capability, but it also reduces our inertia or our frequency. It reduces the frequency response due to lack of inertia because the frequency damping is degraded. And so we would need some solutions there. But strong systems, sorry, Mike. But strong systems with FFR are possible with that emerging technology through grid forming inverters. Battery energy storage systems are highly capable of providing that type of service. And we continue at NERC to monitor and assess and potentially mitigate threats to frequency stability because it is an essential need in interconnected AC systems. And that's my last slide.
All right, JP, hopefully we won't have feedback on the two mics here. Sorry about that a minute ago. We've got several questions that came in. Great presentation. Let me back up to one of these slides for the first question that came in. So this first question, JP, on slide 52, over here on the left, you're showing the initial response of a wind turbine with this fast frequency response. And let me see if I characterize this correctly. You've got basically, looks like you're borrowing some energy here that you can't sustain, so you have a little bit of a drop going past that T nadir, and then it basically levels out at a level close to where it initially was before the event. Is that correct?
That is correct.
Okay, so the question, if that's the case, the question is then based on, you showed us three different response, with the better improved response would be if those 80% inverter-based resource penetration, if it had a 10 millisecond delay here, appears to be much better response versus the 1 second delay, which, as you pointed out, likely just tips into that first under frequency load shedding level. So if that's the case, where does the energy come from? Like if you're borrowing this energy for this 80% of resources for just a T nadir, where are you getting that sustained response to help arrest this event?
Awesome. Thanks, Mike. I mean, that's a great question. Still getting a little feedback from, thank you, Mike. But the one that you highlight with it essentially looks like an isosynchronous control. So it doesn't actually adjust frequency from a synchronous plant perspective, but a wind turbine that has proportional inertia-based FFR can adjust its pitch a little bit to steal some energy off of its actual rotating mass. It's lesser than typically a synchronous machine. And so this would be partially sustained and you'd have to pay that back. And so similar to synchronous machines, you do have to pay that energy back when you take it out of the rotor when you're trying to speed up the rest of the system with an increasing frequency. Now, some of these other responses, particularly battery energy storage, it comes from its stored energy or the DC side of the inverter. So where there is stored energy, you can readily enable an energy burst or an energy injection. And with synchronous controllers, as long as you have intake or feed, and you're able to reconfigure very quickly, like with fast valving and gas plants, you can be able to provide some energy before your nadir, which actually takes more than a second or two to engage. And so with sufficiently fast control, even in synchronous plants can enable fast frequency response. It's not just an IBR place here, but I think that kind of answers your questions there, Mike. But it all comes of where the energy is coming from, and if it's an inverter-based resource, it's coming from the DC side, or when it's synchronous, it's your primary fuel source. So battery energy storage is a chemical response. There's some inherent reaction there, but it is a storage form of energy. Solar PV that's dispatched off of maximum has that capability, assuming that it can enable its maximum power output. And so its MPPT is not at maximum or optimal, but instead is able to reduce its power output and then re-enable that fairly quickly through software control. So there's many different ways to enable it, but it does require pre-planning and design to enable.
All right, JP, I will load up a couple questions here for you, and then I will mute my mic so we don't get that feedback. So give me just a second here. The first one is going to be, at what percentage of inverter-based resource generation do you anticipate we have a challenge with both synchronous inertia frequency response and then later the sustained response without overshooting or undershooting the frequency point? We'll just start with that one.
Got it. Yeah. So I think it's a great question. The challenges of IBR penetration do vary between system to system. So not every synchronous generator is going to have the same impact as it is or is not replaced by IBR penetration. Also, with the major load growth of our system, we're starting to see added generation generally rather than replacement of generation. So I think that there is a unique system by system way that you may have and find challenges. We started to see some in the like 20% to 40% for instantaneous penetration. There's even some success stories of islands operated at 90+% IBR penetration while maintaining frequency stability. So there's starts of challenges early, but there are success stories for controls and implementation of those controls, even at the high 90+% points, to enable that response. And so I think the question of overshoot in the end of that primary frequency response, I think is it's less on re-enabling a separate then droop control, but to add this response to your droop controller. So it does go back to how these things are implemented in the fast frequency response. So if you have it as a summation of your active power into your total injection from the IBR, your fast frequency time domain, if it's non-sustained, would then default back into the droop controller to enable the set points. And so you may have some overshoot, but it is a coordinated type of control by which you're not sustaining or moving into that stabilizing recovery window with an off nominal frequency set point that will be off from a typical droop control. So this wasn't to bash any sort of droop controls, as I think that from a system perspective, having most units on some form of droop control with or without a deadband, depending upon how you're operating, is probably still the best way for frequency regulation in the steady state.
All right, thank you, JP. For this next question, I think we'll make it our last question because we do need to circle back and pick up a couple of our regional announcements that we had earlier. So for this last question, I pulled up slide 51, and you pointed out that those three delays, the TSG, TST, TGS, are cumulative, and you pointed out the importance of those with the time delay. So with this last question is, are you seeing fast frequency response technology included with new inverter-based resources, in other words, with their interconnections? And if not, what can be done to encourage developers to utilize this equipment? And then for that same question, how is this FFR technology going to be pushed out? Is it going to be like dictated by the planning coordinator, or is it going to be dictated by standards? How does that get pushed out?
Thank you. Yes, and all great questions there. I'll answer it kind of piece by piece. I would say we're not seeing essentially every IBR plant being able to enable all components of fast frequency response. And I think that's almost by design. Because fast frequency response kind of needs some sort of stronger system to help damp out some of the controller oscillations, it is largely not implemented in like the pro forma. However, I would think that the best way to roll this out is through transmission interconnection requirements. So those would be housed largely under FAC 1 and FAC 2 of NERC reliability standards for the requirement to develop, post, and then study according to those, whereas FERC does have the pro forma LGIA and SGIA. Now, the IRPS and others have recommended the adoption of IEEE, not 5047, that's on the distribution system, it's where I typically work, so I'm sorry, is actually the adoption of IEEE 2800 2022. So that standard does have various FFR enabled capabilities. And so where we would see the recommendation being rolled out the best would be for utilities in their facility interconnection requirements to adopt IEEE 2800 as part of those requirements. And part of that is ensuring that they have knowledge of their system and identification of either regional or even site specific, if they can get so detailed, types of settings to enable for specific facility interconnection to help support that local system as well as the broader system. And so that will enable fast frequency response if it is done in the facility interconnection requirements, and the transmission utilities are able to identify areas by which FFR capabilities are a great need. And so I think even the past presenter here, Daniel, was sharing that how can we leverage at the right point to inject this energy. And I think the best way to do that is actually through the facility interconnection requirements, because it is going to require in the facility interconnection stage the actual design of the utilization of this energy. And because of all of that, I think where we start seeing NERC recommending is for installers of battery energy storage systems to include frequency regulation and or fast frequency response. And that's where we're starting to see a lot of this take on, is actually in the battery energy storage system area.
Okay, JP, thank you so much. Great presentation. I want to thank you for that, and we will move on to some of our more general comments moving out of this session into that. Thank you so much.